Hello everyone, I'm Shengli Jiang, a third-year PhD student from Professor Victor Zavala's lab. Today I will talk about how we uncover color as a source of information in liquid crystal sensors. The current air quality monitoring infrastructure is limited in spatial resolution due to high cost of sensing equipment and transportation logistics. The equipment cost can range from $1,200 to $12,000, and the equipment is difficult to transport. For instance, there are currently 1,877 ground-level ozone monitoring stations available in the US. This prevents monitoring air quality at localized environments, such as manufacturing facilities, disaster areas, and buildings. Also, usually one sensor can only detect one chemical. To detect multiple chemicals, we need an array of sensors. Because of those 2 points, we need mobile, inexpensive sensors that can detect multiple chemicals at the same time. Liquid crystals are chemically responsive materials that can be used to fabricate inexpensive, wearable sensors, such as the one in the figure. Here is a video of the spatial temporal sensor response to the ozone and chlorine gas mixture. We can see some interesting optical color patterns starting to show up through time. Here we have some screenshots of the video. These sensors comprise of a micrometer thick LC film that is supported on a chemically functionalized solid surface. The chemically functionalized surface is designed to align LC homeotropically, that is, vertically, in an analyte-free environment. When sensors are exposed to gaseous analyte, the analyte diffuses through the LC film and binds to the chemically functionalized surface that disrupts the molecular interactions between the surface and the liquid crystal, resulting in a change in the alignment of the LC from homeotropic to planar. Cross-polarizer microscopy is used to observe the change in the LC orientation. When the LC film is in the initial homeotropic alignment, light is unable to pass through the cross-polarizer, and the image of the sensor appears black. After exposure to an analyte, the LC begins to reorient and refract light traveling through the thin film. The refracted light is then able to pass through the cross-polarizer, resulting in the presence of inference patterns and colors, which are related to LC orientations. Here we have the liquid crystal spatial temporal color response to pure ozone and pure chlorine. We can observe that ozone will lead to a much faster response, that is 30 seconds versus 300 seconds. Also, ozone color response is more uniform, but chlorine response has a moving edge frontier towards the center. Previously, 2 methods have been used to reduce the complexity of the video. One approach is to average spatial information to obtain a time series vector. For example, people have used normalized light intensity to study the LC response. Another approach is to obtain the spatial response. That is a screenshot of the video. In this way, we can study the topological information and the spatial autocorrelation. This graph are the time responses of light intensity and the liquid crystal. The solid line is the average response over many samples, and the shaded area is the standard error. People have demonstrated that the time scale of this response, which is measured by the time required for the image to reach a certain normalized intensity threshold, are directly correlated to the concentration of ozone. Specifically, when we change the ozone concentration, that is, they have the different colors here, the response time changes significantly. However, different chlorine concentration from 0, 1, 2, 5, they have limited effect on the response time. More importantly, the standard error of the response is large. If we use time response alone, we will ignore important information in the spatial temporal color response. Here the figure shows the response of multiple LC sensors to an environment with 650 ppm of ozone and varying levels of chlorine. We can see that these patterns are difficult to characterize and distinguish. Also, these videos contain a rapidly evolving pattern. It is hard for us to find an optimal time to collect the images. For example, images picked at 30 seconds and 35 seconds might give a very different prediction results. In application, it is important that the sensors are able to measure the concentration of both chlorine and ozone, and these components are commonly present together in water treatment facilities and other industrial processes. Therefore, our first goal is to develop a comprehensive spatial temporal data representation of the sensor video. The second goal is to develop a model that predicts both the ozone and chlorine concentrations. The third goal is to uncover important features that go over responses. Now I will elaborate on how we use a 3D convolutional neural network to analyze LC spatial temporal color responses. When I first heard about convolutional neural network, my instinct was that it could only analyze images. However, a convolutional neural network, or CNN, can be applied to any grid-like data. Essentially, the convolutional operation is a weighted sum, and it can aggregate local information. The following two diagrams show how a 1D CNN and a 2D CNN work. That is, sliding the filter and taking the element-wise multiplication and summation. 1D CNNs can analyze time series. 2D CNNs can analyze images. Therefore, 3D CNN can also study videos which have an extra dimension, time. Here, we develop our 3D convolutional neural networks. The important aspect of this dataset is that it is recorded in RGB format, where each image has 3 channels which represent the intensity value of color red, green, and blue for each pixel. By sliding the 3D convolutional filters in the X, Y, and T dimensions, the 3D CNN captures both the temporal and the spatial information. Overfitting has always been a concern with neural networks. Our model has about 10,000 parameters, but we only have 1,000 videos. Therefore, we need to check the robustness of the model. Our dataset has 16 ozone and chlorine concentration combinations, with ozone concentration from 1.5 ppm to 650 ppm, and chlorine concentration from 0 ppm to 5 ppm. We fix the concentration of each ozone and chlorine, and predict the concentration of the other chemical. For example, we fix the ozone concentration at 1.5 ppm and predict the chlorine concentration. To improve the robustness, we use a fourth rotational data augmentation, that is rotating the x1 plane 90 degrees 3 times. We also use a never before seen concentration of 650 ppm and 3.5 ppm of chlorine. Here is a representation of the training, validation, and testing procedures utilized to provide a statistically valid estimate of the performance of the 3D CNN. The entire dataset is split into the independent sets of the training, validation, and the testing videos. The training and the validation videos are used to optimize many parameters of the 3D CNN model. Predictions are then made on the testing videos in order to estimate the accuracy of the model. We are interested in detecting the existence and predict the concentration of chemicals. So we perform the concentration regression and the classification tasks. The first parity plot shows the predicted and the true chlorine concentration. When we fix different ozone concentration, for the never before seen 3.5 ppm chlorine concentration, our results are quite close to the true value. It does not go very high above 5 ppm or below 0 ppm. Shown here are the results of ozone concentration regression. The R-squared value for ozone is 0.96, which is very close to 1. For the classification task, we use the confusion matrix to show the classification results. On the x-axis is the true concentration. On the y-axis is the predicted concentration. The diagonal entries show the density of the accurately classified samples. For example, 0.79 here means 79% of the true 1 ppm chlorine samples were correctly classified as 1 ppm. Chlorine concentration classification was 83% accurate, and for ozone, it was very close to 100%. Although 3DCN makes a good prediction, we want to know what does the 3DCN learns from numerous video data, or is the prediction of ozone and chlorine based on the same or different hidden features? We use the CDC map to learn what are the important things in the data. The idea of a CDC map is that we want to know which grade in the input has a big impact on the model prediction by perturbing a little with the input. For example, if we perturb a little with the input grade A, the prediction changes a lot, say 0 ppm to 5 ppm. We know that the grade A is important. Here are some images that show the areas of CDC or importance for accurate classification. In this example, the CDC map shows the part of the image that makes the model think that the image contains a bird. Here we show the CDC map results for the model prediction. The first one is for ozone prediction. The most important feature for ozone concentration prediction is the response time and the saturation time. It is difficult to visualize and analyze the spatial temporal CDC map, so we average the spatial CDC to obtain the time CDC signal. We can see here that the red line represents the temporal CDC. The black line is the spatially average light intensity of the video along time. The higher the CDC value, the more important the corresponding time is. When we observe that two spikes in the CDC values. One is at 33 seconds, where the response begins. One is at 52 seconds, where the average intensity value is saturated. On the bottom, we have an array of RGB images and intensity images. We can see that the response starts at 33 seconds and saturates at 52 seconds. However, the most important feature in detecting chlorine is the color fluctuation after the intensity value has saturated. Here the red line is temporal CDC. The dashed black line is A star, which is a descriptor to show how red or green the color is. A positive A star means it's redder, and a negative value means it's greener. 52 seconds later, when the intensity value has saturated, we still see several peaks. These peaks are well correlated with A star fluctuations. At the bottom, we also show images of A star. We can see that even after 52 seconds, there are still cycles of red to green color changes. Therefore, the most important feature in the detection of chlorine concentration is color fluctuation. So the color change is related to the change in the LC tilt angle on the surface. We can see when the LC angle starts to tilt, the color changes from black to red, green, and finally to pink and greenish brown. So the next step is for us to understand the physics behind different color fluctuations. In conclusion, we propose a spatial-temporal data representation that can be utilized in 3D CNs. Our 3D CNs can regress and classify ozone and chlorine concentration accurately. Also, we observe that the main driving factor in detecting ozone is the response time and saturation time, and in detecting chlorine, it's a spatial-temporal color fluctuation. After all, I would like to thank all our collaborators from UW-Madison and Cornell, and our funding agency, NSF. Also, we thank the Center for High Throughput Computing for the GPU resources. With that, I'm happy to take any questions.